All right, so we had sort of skipped ahead to chapter 7 to talk about alkenes and to learn about a few reactions of alkenes. Now we're going to go back to chapter 6. Chapter 6 is about building up our tool chest to talk about chemical reactions, so I figured it'd be more convenient to do so within the context of these reactions that we actually learned. Okay, so first of all, okay, if I have an alkene and I treat it with a hydrohalogen like HBr, everybody take a second and give me the products of this reaction here. Product in this case. Oh. All right, so remember these are these addition reactions where you're going to have your halogen added to one side of the double bond and the hydrogen added to the other side. And importantly, these are regioselective reactions where that halogen is going to go on the more substituted carbon. Okay, and here I explicitly drew in that hydrogen. But of course, hydrogens can be implied, so we want to get used to looking at it without the hydrogen there, right? This is our product of this reaction. Cool. So then for this reaction, we also learned not just how to do our products, our substrate reagent product combination, but we also know the mechanism of this reaction here, which is going to involve some intermediate. Take a second and see if you can't remember what the mechanism for this reaction is. Okay, that pi electrons are going to reach out and grab that acidic hydrogen, breaking that hydrogen-bromine bond. Okay, and this creates an intermediate in our reaction here, a carbocation. All right, so we got two steps in our mechanism here. The thing in the middle we call an intermediate. All right, so this reaction here occurs in two steps. Oh, I forgot my negative sign on my bromide. So then in the last step here, we're going to have one bond formation arrow starting at a lone pair on the bromide and connecting to that carbocation. All right, so what we're going to start today is with some terminology here. We didn't use this terminology before, but we're going to use it a lot going forward. In this particular reaction here, my alkene is playing the role of a nucleophile. And the HBr is playing the role of the electrophile. All right, in particular, my nucleophilic site on this molecule would specifically be that double bond that's at the base of my arrow. And the electrophilic site is the thing that's being hit with the arrow, my hydrogen. Okay, so we're going to talk about this terminology real quick because it's pretty ubiquitous over organic chemistry. Nucleophiles and electrophiles. Okay, so first of all, in our mechanisms, the base of the arrows always starts at the nucleophile. And it always ends, the head of the arrow rather, is always at the electrophile. Okay, so what we say is nucleophiles attack electrophiles. Right, this reaction is driven because that pi bond reaches out and attacks that acidic hydrogen. So again, nucleophiles will always be at the base of the arrow. And the electrophiles will always be at the head of the arrow. And we say nucleophiles attack electrophiles. All right, so let's pick these words apart. Nucleophile. Does anybody know what that phile suffix means? Loving, exactly, like a lover of something. So in this case, the word nucleophile comes from nucleus, loving. And what subatomic particles live in the nucleus of an atom? The protons and the neutrons, and so what's the overall charge of the nucleus of an atom? Positive, okay? So something that really loves the nucleus, something that really loves positive charges, is itself an electron-rich species. Nucleophiles are characterized by having this electron density, lots of electrons, right? That's why they want the positive charge. Okay, I'm going to leave some space because we're going to talk a little bit more about nucleophiles here, but just to get through our definitions here, an electrophile, that word comes from electron loving. Right? So these are species that really want electrons. They really want that negative charge. So they themselves do not have electrons. That's why they want them, right? So whereas nucleophiles are electron-rich species, electrophiles are electron-poor species. That's why they want the electrons, right? Because they themselves don't have them. Okay, and this is really the basis of like 95% of all reactions in organic chemistry. You got something with a bunch of electrons, and this other thing that doesn't have a lot of electrons. Why do they react with one another? Because this thing wants this one's electrons, right? That's the driving force behind 95% of all reactions in organic chemistry. One species is electron rich, the other species is electron poor, and that's why they react with one another. Okay, so let's go back up to our intermediate step here. And let's see if we can't figure out who is the nucleophile and who is the electrophile in this step. Everybody take a second. See if you can't label the carbocation and the bromide ion. One of them's playing the role of the nucleophile, the other one's playing the role of the electrophile. Which one's which? All right, so first of all, the nucleophile is always at the base of the arrow. The electrophile is always at the head of the arrow, right? So my bromide ion is my nucleophile. My carbocation is my electrophile because, again, I have my electron pushing arrow in there. But even if I didn't, if this wasn't here, how could I tell that my bromide is my nucleophile, my electron-rich species? Because it's got that negative charge, right? So yeah, absolutely. That one's the electron-rich species because it's got a negative charge. And on the flip side, my carbocation is my electrophile, my electron-poor species because it's got a positive charge, okay? So strictly speaking, in order to be a nucleus, you have to have a pair of electrons to donate. Right? The only way that a nucleophile can do that attacking is to give a pair of electrons. And those can either be lone pairs, as is the case with our bromide ion, or pi electrons, as is the case with our alkenes. Both of those are donatable pairs of electrons. Okay? And so yes, the easiest nucleophiles to spot are those with negative charges. So an example of a nucleophile would again be that negatively charged bromide ion. Another good nucleophile that's negatively charged would be a hydroxide ion. Both of these are electron-rich species that have some lone pairs that they can donate. All right, but they don't have to have negative charges. They can also be neutral. We saw our alkene pi bond is an example of that. All right, water with its lone pairs can also be a nucleophile. Okay, but what do we think would be a better nucleophile, hydroxide or water? Hydroxide. It's got more electron density. So in general, yes, these negatively charged nucleophiles are better nucleophiles, right? But we also want to look for these neutral nucleophiles. We've seen, in fact, this chapter is all about those alkene pi bonds playing the role of a nucleophile. All right, the bottom line is that this molecule just has to have a pair of electrons that it can donate in this reaction, okay? What it's not going to ever have is a positive charge, okay? So they're either going to be negatively charged or neutral. Okay. The other thing just to note here is we talked a lot about acids and bases. A base is a nucleophile. But it's like a very specific type of nucleophile because what is it attacking specifically if it's a base? What are they accepting to be a base? That hydrogen, that proton, right? That hydrogen ion. is a nucleophile that attacks H+. Okay, so we've already talked a lot about a particular type of reaction between nucleophiles and electrophiles. We don't really call them that because if it's specifically protons that are involved in the reaction, we call it a base. All right, but we're going to see a lot of overlap between this world of good bases and world of good nucleophiles. A perfect example is that hydroxide ion. Hydroxide is a great nucleophile, a great electron-rich species that can donate a pair of electrons. We also know it's a really good base. Okay, so an electrophile then, if a nucleophile is going to donate a pair of electrons, an electrophile has to be able to accept a pair of electrons. And so as we saw, one good electrophile, a quintessential organic chemistry electrophile, is that carbocation, right? So a good feature of good electrophiles is that they have those positive charges, as is the case with our carbocation. All right, but we're going to say, be careful. Okay, just because it has a positive charge doesn't necessarily make it an electrophile. Let's look at two examples here. Our carbocation and a hydronium ion. A carbocation is indeed an electrophile. It's a great electrophile. All right, but that hydronium ion is not an electrophile. It's also not a nucleophile because it has a positive charge, but it is neither a nucleophile or electrophile. Why can't that hydronium ion be a nucleophile? What's the, what did I just say? Did I say nucleophile? Why can't the hydronium ion be an electrophile? What's the number one thing an electrophile has to be able to do? Accept a pair of electrons. Can you add another pair of electrons to that molecule right there? No, not without breaking it up its octet rule, right? So yes, it has a positive charge, but it cannot accept electrons. So again, it's going to be neither a nucleophile or an electrophile. Okay, we will also see some neutral electrophiles, never negatively charged, but we will see some neutral electrophiles. But they're always going to have some same common features here. Okay, so one example of a neutral electrophile would be a carbonyl bond. So that's carbon double bonded to an oxygen. Okay, this is going to be a very common electrophile that we see in this course. So why is it an electrophile? Well, first of all, this is a polar bond. So carbon has that partial positive charge, right? There's a partial negative charge on oxygen and a partial positive charge on carbon. That's what it means to be a polar bond. So again, that carbon is left relatively electron deficient. right? It's an electron-poor species. But not only that, let's say that I take some generic nucleophile here. We represent that Nu with its lone pair and its negative charge. This is our generic nucleophile symbol. Okay, this carbon does indeed have a full octet. So if I just draw one arrow here where that nucleophile attacks that electrophile, I can't actually do that, right? Carbon will have too many electrons. Okay? But it's got this polar pi bond. Remember we talked about resonance structures that are available. This pair of electrons can easily jump up onto that more electronegative atom. Okay? So there's this polar bond, that's an important feature, but also it has a pi bond that we can break when that carbon gets attacked. Okay, so carbonyls would be an example of a neutral electrophile. All right, another example would be our alkyl halide. Okay, so again, carbon can be an electrophile in this bond here. So first of all, again, we have a polar bond where carbon has a partial positive charge. Right? Bromine has a partial negative charge. Carbon has a partial positive charge. So step one, it's relatively electron deficient. Okay, if we take that same generic nucleophile and we have it attack that electrophilic carbon, again, I can't stop there. I got too many bonds for my carbon. But what happens is that bromide is considered a good leaving group. So that carbon can get attacked and kick off that bromide ion. So if you have a polar bond with a good leaving group, that would also be considered an electrophile. All right, and so real quick, we now introduced another term here, leaving group. All right, what is it doing in the reaction? It's leaving. I mean, it's not the most creative name in the world. It's just something that gets kicked off. All right, but what makes a good leaving group? What makes bromide a good leaving group? We talked about this, like, why is hydrobromic acid a strong acid? Right? Because that bromide ion is super stable all by itself. It's perfectly happy to just sit there with a negative charge and float around in solution. Okay, so that's a characteristic of a good leaving group, something that's stable on its own. And since we already studied acids and bases, we can think about that as just being a weak base. Or I guess we want to say a very weak base. And typically our halogens are the ones playing these good leaving groups, right? The bromides, the chlorides, the iodides of the world, the things that are really stable all on their own. Okay, so our organic reactions are going to take place between a nucleophile and an electrophile. The nucleophile is the electron-rich species, and the electrophile is the electron-poor species. And again, that's kind of the logic behind all these reactions we're going to study. Something with a lot of electrons reacting with something that doesn't have a lot of electrons. The nucleophiles tend to be easier to spy, okay, because it's just anything that has a lone pair that it can donate, especially if it has a negative charge. That's a good nucleophile, okay? Electrophiles are a little harder to spot. Our carbocations are going to be a quintessential electrophile, but we can also see some neutral electrophiles if they're polar with pi bonds or polar with good leaving groups. Okay? And again, in your mechanism, your electrophile is always going to be the one that's at the head of the arrow. Right? The nucleophile is doing the attacking. That's at the base of the arrow. Cool. So we're going to use this terminology a lot here, nucleophiles and electrophiles. All right. So now, again, just sort of overview of chemical reactions. Let's ask ourselves, why do chemical reactions occur? And like, don't get me wrong, that is kind of like one of the hardest questions that you could possibly ask in chemistry, right? But we see certain patterns over and over and over again that reactions that occur spontaneously have. Okay? So first of all chemical reactions have the same sort of features where you have bonds that are breaking. Right? Chemical reactions, we make and break bonds. So, one common feature, we got bonds breaking, and in order to break a chemical bond, in order to break a covalent bond, we have to input energy. Right? You got to put energy in order to break a bond. But then new bonds are formed, right? So you break old bonds and then you make a bunch of new bonds. And bond formation does the exact opposite. When new bonds are formed, that releases energy. Okay, and so one common feature that we see over and over again with our chemical reactions, that are spontaneous reactions, these reactions that actually do go forward and create products, is that the amount of energy released is simply greater than the amount of energy you have to put input. Right? So the universe, we got matter all organized, right? If we're performing a chemical reaction, we're changing that. We're breaking old bonds and making new bonds. So why is the universe like, yeah, let's do that. Let's go ahead and do that. Because the amount of energy you have to put in to break those bonds is less than the payout that you get, right? There's more energy that's released in this process when those new bonds form. So a lot of these chemical reactions that will occur spontaneously, you're breaking weaker bonds than what you're forming on your other side, on the product side. Okay? What's up?
I was going to ask, so it's the output energy from bond formation, like it releases energy because it turns into a more stable version of itself, right?
Yeah, so if two things are going to form a new bond, that's going to be a favorable event, right? Now they get to share their electrons. Everybody wants that complete octet. So yes, so the only reason that two atoms would bother bonding together is because they'll reach a lower energy state when they do it. They'll release energy when they do it. Otherwise, they just won't form the bonds to begin with. Okay? All right, cool. So this is going to now segue into what's called bond dissociation energy. All right, this bond dissociation energy is the energy required to break a bond okay, but specifically using what's called homolytic cleavage. And we're going to see that like this kind of doesn't even matter here, but let's talk about what that means real quick. Homolytic cleavage is taking a bond and breaking it straight down the middle, chopping it in half. All right, so let's say I have a bond between two atoms A and B. A homolytic cleavage is chopping that bond straight in half so that A gets one of the electrons and B gets the other electron. So an even 50-50 split of that bond that used to be shared between the two. What do we call these unpaired electrons? Does anybody remember? We talked about it first when we were talking about mass spec. It's got, yes, exactly. These are called radicals. Now, we've talked about the mechanisms of these reactions that we've studied thus far, and none of them go through a radical pathway, right? There's not any radicals involved here. Nonetheless, energy is kind of this magical thing where if you start in one place and end in another place, it does not matter what path you take to get there, all right? So these energies are what are called state functions. They're path independent. So it turns out that if a reaction happened through a radical mechanism to get to products, or it went through a different mechanism to get to those products, the difference between those two energies is going to be the same. So even though none of the reactions we study are going to go through this homolytic cleavage pathway, we can still use these bond dissociation energies to predict how much energy is going to be released or maybe not happen, will be absorbed in a given reaction. Okay? All right, so let's do one example here. First, we're going to write it all out with our, so this will be one that we've talked about before. What if we take ethene, just a nice small alkene, we're going to combine it with diatomic bromine. Okay, everybody take a second and give me the product of this reaction here. Right, so again, we have this addition reaction, but this time it's Br2, so we're going to get a bromine added to both sides here. Okay, and now we're going to calculate the amount of energy that's released when we first break these bonds, but then make these new bonds. All right, so to do that, first of all, let me introduce you all to our constants page for this chapter. It is this chart here of bond dissociation energies for a bunch of different bonds. Okay, so if we just kind of want to zoom in to a portion here, this D, this is the dissociation energy. So for a hydrogen-hydrogen bond, you would have to put in 436 kilojoules in order to break this bond right here. Okay? Likewise, if you formed a new hydrogen-hydrogen bond, it would release 436 kilojoules of energy. Notice we can sort of look just curiously at like our relative bond strengths here, right? Look at the bond between, for example, two iodines compared to two hydrogens, quite a bit weaker, right? So those halogen bonds are easier to break than a hydrogen-hydrogen bond. All right, so going back over here, we need to go ahead and figure out what bonds are being broken in this reaction. We need to highlight those, and we need to highlight which new bonds are being formed in this reaction. All right, because we got to look up each of those bonds on our table. All right, what bonds am I breaking here? Does anybody see one? So I got this carbon-carbon pi bond here that's going to be broken. What else is going to be broken in this reaction? The bromine-bromine bond, right? So I got to look up those, figure out how much energy is required to break those bonds, and what new bonds are being formed in this reaction. Carbon-bromine bonds. Boom. Okay, now, there's one problem here. If I go and I look on my chart here, I won't find the amount of energy required to break just a pi bond. If I look here, and we're going to use this box a lot here, but if I look closely here, this isn't just the energy required to break this pi bond, but to chop this whole friggin' thing, boom, in half here, to break both the pi and the sigma bond in that compound, okay? And I can't like just take this 728 and divide it by 2, because actually pi bonds are weaker than sigma bonds, so that wouldn't give me a correct number for how much energy is required to break that. But what we're going to do is we're just going to pretend in our reaction here, because again, it doesn't matter what path we take, we're going to pretend in this reaction that we break both of these bonds in our alkene. And then on the other side, we reform this new carbon-carbon sigma bond, right? And that'll give us the same energy as if we just predicted that we broke the only pi bond to begin with, right? But because of our chart here and what we have available to us, we're going to say we break the entire pi bond and then reform that carbon-carbon sigma bond, okay? So in terms of values I'm looking up, first of all, I need that one. I don't remember what it is, 728, 738, something like that. 728 for my pi bond. So let me just go back and put that on there. This one was 728. Let's look up our bromine-bromine bond. Okay, everybody take a second and see if you can't find where that would be. The 194, right? So here we go. We're going to grab that value. That's another bond broken. Okay. So now for this one, we have a 2-carbon molecule. And so we got to be careful here. So for example, let me just show you. We got a few carbon-bromine bonds here. This would be for a methyl carbon-bromine. This would be for an ethyl carbon-bromine. This would now be a secondary, like a propyl carbon-bromine on that second carbon. And then finally a tertiary carbon-bromine bond. So which one do I want to use to best approximate my molecule here? How many carbons we got in our molecule? 2. And is it like a secondary carbon we're putting that bromine on, or a tertiary carbon we're putting that bromine on? No. So we're just going to use this value here. So 293. Right, so for your carbons, you got to pay attention to the size of their molecule. Here, we're going to use that 293 value for both those carbon-bromine bonds. Now, if you look, it's not like it changes too much. Like if you used methyl, it's 294, right? It's not like it would be a ridiculously horrible approximation, but nonetheless, we want to do as best we can. So just pay attention to the substitution on your molecule when you're picking your bond here. Likewise, for my carbon-carbon bond, I again want to just use the fact that I'm talking about a 2-carbon molecule. Right, so we're going to use this. Now, I don't have my bromines on here in this formula, right? So it's not going to be exact, but we're just using what we can to get to the best approximation that we have here. Okay, so again, my carbon-carbon bond for a 2-carbon molecule, I already forget what it is, 377, okay. Cool, so now I just got to total up how much energy I have to put in to break both of these bonds. My 728 plus my 194. I need to put in 922 kilojoules to break those, to break a mole of them. Okay, and then my 377 plus my 293s give me 963. All right, so if I have to put in 922 kilojoules, but then I get out more, right? That's the whole shtick. That's why these reactions like to happen, is because I get out more energy than I had to put in. Okay, so what we can calculate, the difference between these two, is what we call delta H, the enthalpy of this reaction. The enthalpy of this reaction is going to be the sum of that dissociation energy of the bonds you got to break minus the sum of that dissociation energy of the bonds that are formed. So I'm going to take my 922 and subtract my 963. Gives me a delta H of negative 41 kilojoules per mole. All right, hopefully this is a callback to Chem 1B for y'all. Enthalpy. Spent a lot of time discussing one of those main thermodynamic variables. So that's what we can predict when we use these bond dissociation energies, is how much heat is going to be absorbed or released when these new bonds get broken, when these old bonds get broken and our new bonds get formed. Okay, so now we're going to introduce a new reaction here, another addition reaction. What's called a hydrogenation reaction. This is the addition of hydrogen gas to an alkene. All right, so again, let's take our simplest alkene that we got, ethene. And I want you guys to see if you can't predict the products of this reaction here. We've never talked about this reaction before. But what I'm going to tell you is that it is an addition reaction. Tell me to see if you can't predict the products of this hydrogenation reaction. Alright, so all I'm going to do is add my hydrogen to either side. So what does our hydrogenation reaction do? Converts an alkene to an alkane. Cool. All right, so now let's go through, figure out what bonds are broken and what new bonds are being formed. So we can calculate the enthalpy of this reaction here. All right, so we got to break our alkene bond and our hydrogen-hydrogen bond. We're going to reform that sigma bond between our two carbons, and now we got two new carbon-hydrogen bonds. All right, so these are what we're going to have to look up on that chart here. Okay, our chart's kind of big, so let me go to the top first. Okay, you should be able to take all of your bond broken values from this portion of the chart. Okay, so just take a minute to find those and take note. All right, and then you should be able to get your bond formation values, the new bonds that are being formed from this portion of the chart. All right, so my hydrogen-hydrogen bond was 436 kilojoules, whereas my carbon-carbon double bond was 728. Add those both up, and I'm going to have to put in 1164 kilojoules to break both of those bonds. On the flip side, my new carbon-carbon bond that forms is going to release 377 kilojoules, and my carbon-hydrogen bonds are going to release 421 kilojoules. Okay, to be clear, where did I get that 421 from? All right, I was looking at a 2-carbon compound and the bond energy of that carbon-hydrogen bond. So sum that all up, and I will release 1219. So then my delta H is the amount of energy you got to put in to break minus the amount of energy that's put in when that's released when those new bonds are formed. And so I get negative 55 kilojoules per mole for this reaction here. Okay, so again, delta H is what's called enthalpy. All right, importantly, we got some fancy terminology here. When delta H is less than 0, a negative value of delta H, we have a specific name for those type of reactions. Does anybody remember? These are exothermic reactions, meaning they release heat. We have another name for when delta H is greater than 0. Does anybody remember what that one is? Yeah, endothermic. Which means that the reaction absorbs heat. And again, we can predict the value of delta H by using those bond dissociation energies, and that's really helpful because the vast majority of reactions that occur spontaneously are exothermic. All right, so a negative value for delta H is a favorable reaction. All right, and I kind of built in like a little bit of a caveat here. I didn't say all reactions, I said the vast majority. Right? 99.9% of the reactions we study are exothermic reactions, reactions that are favorable because the bonds that are formed are going to release more energy than you had to put in to break those old bonds. Okay? But this isn't strictly true in terms of how we look at reactions and predict whether or not they occur. We got to review. First of all, let's take this reaction real quick. I'm just going to summarize. Ethene, which is a gas, plus hydrogen, which is a gas, gives me ethane, is also a gas. And we said the delta H of this reaction was negative 55 kilojoules per mole. All right, so first of all, this reaction here is a reaction that does occur spontaneously. We would consider this a spontaneous reaction here, but nowhere near to the degree that that value of delta H predicts. That's a huge number for delta H, and it turns out that this reaction is not quite that favorable. All right, so why would that be? Okay, we got two things going on here. Enthalpy is a big one, okay? But remember, the real measure for whether or not a reaction occurs is not just enthalpy. It's what we call free energy, delta G. Okay, and delta G literally tells you, does this reaction occur or not? That's what the value of delta G tells you. All right, and enthalpy is certainly a big component of delta G. But it isn't the only component. Does anybody yet remember what's the other portion of this equation here? What else does delta G depend on? Delta S, all right? So the real equation here is delta G equals delta H minus T delta S. We talked about delta H is enthalpy, but delta S is by far the weirdest quantity of energy that you will ever encounter in your entire life, what's called entropy. Okay, and entropy is this energetic push towards disorder, towards a more randomized, more disordered state. All right? Entropy is the weirdest force in the entire universe. I remember being a young chemistry student and hearing like, oh, energetic push towards disorder, and being like, okay, all right. I can't wait till I get to like upper level chemistry and I actually understand what the heck that is, because they're definitely lying to me. And then you get to upper level chemistry, and it is indeed just the universe likes randomness. It is their energetic push towards disorder. For every reaction, if it creates a more disordered state, the universe likes it. It wants to spread out all the energy of the universe. Turns out that all the universe is doing constantly is trying to spread energy out to all corners. Right now, if we look really, really big picture here, we got really dense pockets of energy and stars and galaxies and all that stuff. Well, at the end of time, when we'll be long, long gone, the universe is constantly pushing to just spread that energy out evenly. And so there will be a point where our universe dies because every bit of that energy that's currently concentrated in little pockets all over the place will be spread perfectly evenly throughout all corners. It doesn't make sense. I mean, it's cool. Like, no, who knows? Why? Okay, but bottom line is, yes, there is an energetic contribution, a literal measurable amount of energy that's dedicated towards pushing stuff towards randomness, okay? So chemical reactions that create more disorder are more favorable, and chemical reactions that create order, that organize stuff, are less favorable, all right? The universe doesn't like order. It's mad about it, all right? We are very ordered species here, right? I mean, just the fact that we exist is like super crazy and entropically unfavorable. And how do we get away with it? Because our body is like constantly taking energy from other sources. It's ending up creating energy through heat and all this other stuff, right? So us just being here, the universe is mad about. And we got to give up in many other ways to let it happen, all right? Mostly through the food that we eat and then the digestion process that breaks it down and releases heat and all that stuff. But yes, so why is this reaction here nowhere near as favorable as it looks just by looking at that delta H value? Is because here we have two gases and they're being made into just one gas. That would be considered creating order. The universe is mad about it, right? So this reaction, while it's exothermic, which is again very good, it is got a positive delta S, which we would say is entropically unfavorable. Okay? Now, in Chem 1B, you did a lot of math with this equation. We're not actually going to do math with this equation. It's not about looking up those values in the standard states and all that. But we are going to look at these free energy diagrams. We like to characterize reactions based on their free energy because, again, that tells you whether or not the reaction actually occurs. All right? Entropy is something that's kind of easy to predict for reactions that happen in the gas phase. Like if you're taking more gas molecules and making them into fewer gas molecules, that's entropically unfavorable. Or if it's the reverse, if you take a few molecules and make them into many, the universe likes that. As soon as you get to like the liquid phase and solutions, it becomes really kind of counterintuitive because you talk about the entropy of not only the reaction, but what's happening in the solution with the water molecules interacting. Anyways, our like kind of common sense perception of things kind of goes out the window when we're talking in solutions. All right, but for our delta G here, again, we have some fancy terminology. What we want is a reaction where delta G is negative. This would be a reaction that occurs spontaneously, which is a fancy way of saying it actually happens, right? You mix this together and you mix that together. Does this reaction occur spontaneously? That just means yes, you do get product on the other side of it. Okay, we have a fancy word kind of like for exothermic delta G's that are negative. We call these exergonic reactions. If you have a delta G that's positive, a delta G that's greater than 0, we call that a non-spontaneous reaction. Which is, again, just a fancy way of saying no reaction occurs, right? You mix this together and that together, and it's a non-spontaneous reaction, you're not going to get anything out of it. Right, and again, fancy terminology, these are called endergonic reactions. Okay, and then just the last thing to review here. In Chem 1B, spent a lot of time talking about equilibrium constants. When we build our equilibrium constants, what do we remember? What over what? No? Y'all really don't know? All right. Products over reactants. Yeah. Products over reactants. So if I have a reaction and let's say that the KEQ is 10 to the 7, some really big number here, does that mean I have more products or more reactants? In order for this number to be really big, what has to be bigger, top or the bottom? The top. So a big K is something that favors the products, right? So a KEQ greater than 1, we say favors the products. And if KEQ is less than 1, it's the opposite. That's a reaction that favors the reactants. All right, and you would have learned about this relationship between KEQ and the delta G. All that to say that an exergonic reaction means that KEQ is greater than 1, right? If delta G is negative, KEQ is going to be greater than 1. Again, this will be a reaction that proceeds in the forward direction, proceeds towards your products. And an endergonic reaction, a non-spontaneous reaction, means that K is less than 1. All right, so these are all sort of one and the same thing here. A negative delta G, a spontaneous reaction, an exergonic reaction, or a K greater than 1, those are all, from a thermodynamic standpoint, saying the same thing. A reaction that will actually proceed towards the product side. A non-spontaneous reaction or an endergonic reaction, those are both saying that you have a KEQ less than 1, or a reaction that favors the reactant side. All right, so next time we'll talk a little bit more about this free energy. We're not going to be doing any math, but we are going to be looking at these charts, which I think you've probably seen before. These little like free energy diagrams, these little curvy things. That's kind of the extent to which we need to review these thermodynamic variables, because we want to be able to look at these charts for our reactions and get information from. All right, cool. So we'll pick up at